So in the previous video I covered emulating the 48K spectrum using C, and in this video I'm going to show what's required to do the bank switching which is needed to do an emulation of the 128K spectrum. So everything prior to this is covered in the 48K spectrum video, but this will just cover the bank switching. And also I've created a virtual ZX printer which I'll also demonstrate in this video. So first of all I'll demonstrate the actual emulation running, and then I'll go through the actual theory of using bank switching to switch memory on the 128K spectrum, and then finally I'll go through the source code and actually show how it was done in this particular instance on the source code. So if I start the emulation, and it comes up now with two windows. I've got the virtual printer on the top here, and I've got the actual 128K spectrum being emulated here, and so it comes up with the menu which you get on the 128K spectrum. And you've got the 128K basic, so if I go into that, and you can just type a program like you would on the 128K spectrum. And that all works fine. But to actually demonstrate the virtual printer, the Sinclair printer, you can't do that in the 128K basic, because the 128K basic uses the RS-232 port which was introduced on the 128K spectrum, and so it won't actually output stuff to the ZX printer. So in order to do that I would need to come out of 128K basic and go into 48K basic, which does support the ZX printer. And if I just type in a simple program, something on, because there's three commands which actually can be used for the ZX printer. So I want to produce output that I can actually use to demonstrate all three things. And if I just output the character set like this, then because the first command is copy, and what that does is copy what's on the screen. So you could draw a picture on the display, and then if I just type copy, and that then copies the display and sends it to the actual ZX printer on the right hand side there. The next command is list. So list will generate the listing on the actual VGU display, but list sends a listing to the printer. So if I hit enter on that one, so you get the listing going to the printer. And then the third command that you can use for the printer is, if I can remember the key, lprint, and you can just send a single line of text to the printer using lprint. So that demonstrates the virtual ZX printer that I've put into this. So the ZX81 supports it, the ZX Spectrum 48K and the 128K models, but only in the 48K mode will support it. And when you're in the 48K mode, you're kind of stuck in that mode. If you hit new, you just stay in the 48K mode until you actually do an actual reset. So if I do a reset of the actual CPU, it goes back then to the 128K menu. So to explain the theory of the memory bank switching which is used on the ZX Spectrum, the 128K models, first of all, to understand the Z80 CPU memory space. So the Z80 CPU can only handle addressing 64K of memory, whatever type, whether it's RAM or ROM, in its address space. So any particular instruction in the Z80 can only access that 64K directly. But if I go on to the next screen, and the 48K model, then if I take that over the top of the Z80 model, so you're only accessing 64K for the 48K model. So the first 16K is the actual ROM of the 48K spectrum. Then you get what they call the VRAM, which is the video RAM, and is used to display stuff using DMA. So the CPU accesses it to do programs, and the actual hardware uses direct memory access DMA to actually display stuff directly from the memory without the CPU needing to actually send stuff to the display, like in previous models of the ZX computers. So the ZX81 and the ZX80, both the CPU actually wrote to the display itself, and it used CPU time to do that, but in the Spectrum it doesn't. The Spectrum actually DMA is used to display things straight to the display without the CPU getting involved. So the VRAM itself, that 16K, I've made it a different color because it's actually slowed down slightly, because when the DMA accesses it, the CPU can't, and when the CPU accesses it, the DMA can't. However, it's much faster than the CPU doing the work of sending stuff to the display. But the memory below that, which is 2 lots of 16K of RAM, which is in the 48K models of the Spectrum. So anything above that is only in the 16K models. Then the 48K models had this extra 32K of RAM on it, and that RAM is faster RAM because the DMA doesn't access that, so the CPU can run a lot faster when it's accessing that memory. So the 48K Spectrum actually uses the full 64K memory space available to the Z80 CPU, and it doesn't need to do any bank switching because of that, so everything can be addressed directly from the CPU. But if I go to the next slide, so this is the 1 to 8K Spectrum memory map. Now it uses the full 64K address space of the Z80 CPU. So in the top 16K is still the ROM image, but now there's two ROM images which can be placed in that top area of memory. So the new ROM, which is the 128K basic ROM, and then there's the original ROM, which can be switched into that area when they want to just run the 48K Spectrum model for backward compatibility. So below that is the VRAM. So the VRAM is still in the same place for compatibility with the 48K Spectrum, but it can be bank switched between banks 5 of the RAM and bank 7 of the RAM. So I guess they did that so that when you use the 128K Spectrum, you can actually display stuff or prepare stuff for display in one of the banks, maybe bank 7, and then when you actually want to display, you can quickly switch to that, and that reduces flicker on the display. So that might be the reasoning behind having 2 bits of RAM which they can switch into the VRAM area. Then bank 2 of the RAM is always in that location from 8000 hex to C000 hex, and then the bank switching of the RAM itself for actual programming use is always in the top area of RAM from C000 to FFFF. And so you've got banks 0, bank 1, 2, 3, 4, 5, 6 and 7 of RAM. So there's none of the ROM can get switched into here, but all of the RAM can get switched. So the 128K can get switched here, including the video RAM and the bank 2 RAM, which is also in the already switched into the physical areas above this area for bank switching. So that's how they actually do the bank switching. They use an output port on the actual Z80 CPU to actually switch the physical RAM, but when I go through the source code, you'll see how that actually is happening. So the actual programming of the actual bank switching of memory, the first area to actually look at is the main routine for C. So here, where the entry point for the actual program, and this is where I set up all the hardware. And the way that I actually went about solving this was actually quite convenient for me, because I'd already put in place mirrored memory for the ZX81 and ZX80, where they use mirrored memory to actually drive the display. So I can remake use of that, because here I set up the banks of memory by mirroring the memory into higher memory. So previously on my emulation, I only allowed 64K of memory area, but I expanded that for this support of the 128K Spectrum into much higher areas, and I can mirror that memory into the lower memory areas like I'm doing here. So I've got the 4 memory areas that you saw on that diagram all set up as mirrored memory, And I can then, what I also added was the ability to remap memory. So when the actual the Spectrum ROM decides it wants to bank switch a piece of memory, what it can do is it can remap any one of these areas to the new memory that's required. And I'll show you that in just a little while. Just go through the rest of this initialization. So also the ROM can be mirrored as well. So I've got loading the two ROM images for the old Spectrum 48K and the new Spectrum 128K into different areas of memory. So that by default the 128K ROM goes in at address 0 because that's what gets booted up, and the 48K gets loaded quite high up in memory. And what I can do is I can then bank switch this into the low memory without having to move lots of memory around. So all the actual bank switching process is just actually pointing one piece of memory into another piece of memory rather than actually copying physical memory all the time backwards and forwards. And so this is the end of the initialization for the actual emulation, and I also have to add here a callback for an IO port on Z80 CPU. So if you watch the previous videos, you see I've got port assignments for keyboard, and in the other ZX80 and ZX81 there's a vertical sync port assignment which wasn't required in the Spectrum. But now I need one for page switching. So when the actual ZX Spectrum ROM wants to page switch, it outputs to this port and tells the hardware how it wants to page switch. And also I've got one for the printer as well. So the printer's got a physical port, and I actually just plug that in using one of these callbacks, and that's off in a printer source code which is held specifically just apart for the printer stuff. And as usual, when I'm mirroring memory, I'll have to free up the allocations at the very end of the program before it exits. And so in the emulation, if I scroll down a bit, we get to the actual bank switching callback. So I've confused the terms page switching and bank switching. They basically mean the same thing, but usually in a later computer you get page switching, but this is like bank switching for the CPU, but never mind. So in here it decides on when there's an output from the CPU, when the actual Spectrum ROM says I want to bank switch, it then takes the actual information which is passed from the CPU and decides how it wants to bank switch. And you can see here under certain circumstances it will remirror the memory. So this is a function I've added. So previously I only had to mirror memory at the very start of the emulation because that physical memory was always just mirrored exactly the same way. But now, because of the bank switching, it can actually remirror the memory when it needs to remirror the memory. And so that's all that this actually does. And I've put some comments in. So this is for bank switching the video memory, and this is for bank switching the top part of memory. And it just does it on an algorithm as to how it gets remirrored. And so in the actual hardware emulation, which is this file, that's all that needs to be done here. So it actually wasn't that much more programming required to emulate the 128K Spectrum than it was to emulate the 48K Spectrum. So in the Z80 emulation, when I want to mirror memory, I just, in this function here, I create a linked list, or add an item to a linked list of memory locations which are mirrored. And then before I access actual memory, it just checks this linked list to see if the memory I'm accessing is within the mirrored memory, and decides where the actual memory is to come from, which I'm actually accessing. So this mirror memory is just creating the linked list, and then this remirror memory just below it is reassigning an item within that linked list. So it doesn't actually, so it just updates the values within that linked list which are pertinent to the place where I'm remirroring memory, just to the new address range which is going to be mirrored. So finally, this is the virtual ZX printer source code, and there's not actually much to it. So there's an initialization function. So I'm using X windows to actually display the window like I do with the actual emulation of the computer itself. So in here, all it does is create a window and then decides what actual events for that window it wants to actually handle. So I've got key presses and key releases, but actually I'm not actually handling key presses or releases in that actual window. So actually this is just because I copied and pasted it from my actual emulation of the emulation window. And so it also creates an image area which it displays within the window, and that image area is like I do with the actual emulation of the computer. I just plot points on that actual image. So the initialization of the printer just creates a window, puts an image within that window, and then I've got an exit function which cleans things up before it returns to the operating system, and it just frees up any X Windows resources which have been allocated. And then it gets down to the actual, this is the emulation part. So this is the callback function, which when the CPU does an output or an input on the printer port, so there's only one port for the ZX printer, and this is the callback which gets called when that happens. And so for each time this gets called, whether it's an input or an output, it increases the pixel position on the printer on the x-axis across the printer. And when that gets to the maximum for the actual printer width, it then does a line feed here and tells and returns the result to the CPU saying, okay, you're now on a new line, so that the Spectrum ROM can say, okay, we're on a new line, so we now have to handle output in the next line. So that's the line feed. And then apart from that, if it's an output and the actual CPU, the Spectrum ROM is telling us it's outputting a pixel, then we just plot that pixel on our image, and that's basically the emulation. So I've got some functions, support functions here. The printer feed, so all it does is does a memory copy of the image buffer, so it just scrolls the image buffer up by one effective pixel. So at the minute I'm displaying it scaled 2 times, so it will be scrolling up by 2 pixels. So that's all that does, and it does that just by using a mem copy, and then it outputs that updated image to the window. And then as a printer reset, I don't think I actually use this, but if it wanted to clear the printer, the actual window of all graphics, and just put it back to a blank window, then it would call that, but I don't think I actually call that. And then there's the actual plot function here. For some reason I can't scroll to the bottom there. And okay, and all that does is it decides where it needs to plot on the actual image area, because it can be scaled, so it's scaled at 2 times. It has to do these 2 for loops to do the width and the height of the actual pixel, but then it just plots those pixels onto the image area. And the emulation of the ZX printer is as simple as that. So there's not actually much code to do at all to support the ZX printer.